Hello. I know you've all seen one of these, a cell, or commonly called a battery. Now in today's video, or this video lesson, what I want to do is to deal with the little number that you can see here, 9V, 9 volts. That's actually what we call the potential difference between one point here and the other. So in the lesson today, what I want to do is explain what, first of all, we mean by electrical potential, and then what we mean by potential difference.
Now, let's imagine we've got here a charge Q, positive charge, and away from Q, we've got a distance. And what I start to do is move a positive charge from a huge distance away. Let's call this infinity. And I start to push it, push, because we've got repulsion here, you see. I've really got to push hard. And I push it to here. What I've done is I've used some energy. Now I'm going to call this point here, where I've got the charge, point A. Now at this stage we can talk about the potential at point A. Now the potential at point A is the work done in moving unit positive charge, in other words 1 coulomb, from an infinite distance away to this point. And I'm going to write here V. V is the potential, and that's equal to the work done per unit positive charge. So this charge here was 1 coulomb, and it is KQ. Now the Q is this charge here, okay, that I'm pushing this coulomb against, and D is the distance from here to here. Now the smaller this distance is, the bigger this number here will be. In other words, the greater the potential. The smaller the distance, the greater the potential. I'm just going to call this DA. Okay, so DA is the distance from here to this point here. Now, I'm going to get this coulomb, I'm going to push it to here, to point B. Now, if we talk about the potential here at point B, obviously that is the work done to move unit positive charge, now 1 coulomb, from an infinite distance right out here, right out in space, okay, from here to here. So that's amount of work is KQ on D, and I'm going to call that dB. Now notice that it's D, and it's not D squared. D squared, you remember, is in Coulomb's law. So we've got the potential at A, and we've got the potential at B. So this is what we're talking about when we're talking about the electrical potential. It is the amount of work done, the amount of energy that we require to use in moving unit positive charge, 1 coulomb, from an infinite distance away to this point in the electric field. Okay, so this electric field radiating out here from our positive charge, we have to do some work in order to move our unit positive charge to this position. So that is what we mean by electrical potential. Question: which spot here do you think is at a higher potential? B or A? Now, if you said B, you're correct. B is at a higher potential, and this is at a lower potential. Now here we can see how we could work out the potential difference between B and A. The potential difference between those two would be the potential at B minus the potential at A. So this would be K Q on B dB minus K Q on dA. Now the units there of course would be volts. The unit here for potential is volt, is the volt, and here is the volt of course. So we measure electrical potential in volts, otherwise known as joules per coulomb, and we measure potential difference in volts, joules per coulomb. So if it took me, let's say, 10 joules to bring that unit positive charge from here to here, and then to move the unit positive charge from an infinite distance away to B, it took me 30 joules. Then obviously we're looking at a potential difference there of how many? Obviously it would be 20 volts, or if you like, 20 joules per coulomb. Now, another thought to keep in mind is what we mean by high potential and low potential. Now, if I said to you one of these is at a higher potential, which one would it be? Which one would be at a higher potential, electrical potential? Well, you'd be correct if you said that the higher potential was at B. Now what that then means is, if you keep it, let's imagine we've got our positive charge here, and I let this go. What would happen is spontaneously it would move from here to here to wherever it wanted to go. So this is what happens with positive charge. Positive charge in an electric field will move from a position of high electrical potential down to a position of lower potential. That will happen spontaneously. Now, of course, if we have a negative charge moves spontaneously from a position of low potential to a position of higher potential. Now, when that happens, energy is released. Well, in this particular case, if the charge went from here to here, what would happen is that this, well, let's call it an electron, this electron would gain energy, it would gain kinetic energy. Now, another situation in which we need to consider potential and potential difference is between parallel plates. And what I'm going to do is draw some parallel plates here, and what I'm going to do is use a ruler, and this will make my diagram very neat. That's it here, hopefully. Okay, I've smudged it there. Okay, so there's one parallel plate, and I'll draw another one. I haven't done this terribly well, but anyway, here we go. Over here, but gee, doesn't straight lines make this look neat? Okay, so there we've got two parallel plates, and I'm not going to white that out, but anyway, so there it is. Let's put a positive charge on this plate, and let's put a negative charge on this plate. Now, if I put a positive charge here in between these parallel plates, and I said that the potential difference between these two here was 12 volts. Could I say anything about the electric potential at this point? Very difficult, because the electrical potential is the energy required to move unit positive charge from an infinite distance away to this point. However, I can say something about the potential difference between this plate and this plate. What it means is that there is a difference of 12 joules per coulomb between here and here. So if we had, say, our positive charge up here and we let it go, it would go sailing down here, and that would gain, that unit positive charge would gain 12 joules. So it would move there from a high potential to a low potential. And again, if we had a negative charge here, that negative charge would move from a position of low potential to a position of high potential quite spontaneously, and gain energy in the process. Now, another thing to keep in mind when we're having a look at potential and potential difference is the idea of equipotentials. Now, equipotential means a position or two positions that have the same electrical potential. If I drew a neat straight line here between our parallel plates, all along here, because they're the same, this is the same distance from here to here, all along here, we would say that any charge along here is at the same electrical potential, and we call that equipotential. Now, the similar kind of thing goes for if we have a charge like this, and around it we have a sphere. Okay, that sphere is, or any charge on that sphere there is at as the same potential. In other words, it's a sphere of equipotential. So that's it. This is the difference between potential and potential difference, and the units for potential are volts, otherwise known as joules per coulomb. The units for potential difference are also volts, otherwise known as joules per coulomb.